Hello everyone, my name is Jan. I will present the paper titled Adapted Patches for Mesh Denoising. I will start giving an introduction, then I will talk about some previous work, then I will introduce our main contribution, which is the computation of adapted patches. Then I will talk about our denoising algorithm, then I will show some experiments and results. Finally, I will give our conclusions and future work. So, mesh denoising is related to remove noise while preserving details by modifying vertex positions. This is a challenging problem so far because it is difficult to distinguish high frequency features from noise. A denoising step is typically introduced in a geometry processing pipeline. So, for example, we have this mesh represented in 2D, and this is representing a flat region. We have to modify the vertex position such that the result has less noise than the initial input. This is an example where we have a noisy mesh and then we filter this mesh by a denoising algorithm and we obtain a more clean mesh. Early methods try to remove this noise by smoothing the surface, but the problem with these methods is that they do not preserve the details. Several methods try to reach anisotropy by extending this operator or proposing different filters, but we are interested on two-step based methods where the first step is related to remove the normal field and then update vertex position to fit the faces to the corresponding new normal field. So this is an example where we have the normal field of this mesh. We first consider the normal field, we filter it, and then we adapt vertex positions to fit the faces to the new normal field. We propose to solve the problem of detail preservation by using adapted patches. If we have a reference face in blue and we have a regular patch in red, the average normal of the regular patch is pointing in an incorrect direction because one part of the patch lies in one face and the other one in the other face. But an adapted patch will lie on just one face of the shape, and the corresponding average normal is more accurate regarding the desired normal. So let us represent the mesh as a two-manifold X, where X prime is a subset of X and represents a patch. Using as reference points the lowercase x prime, which is also contained in X. We aim to find an optimal subset X prime such that this subset must be adapted to the shape, must be invariant to noise, and must minimize normal variation. For example, if we have a flat region, the normal variation will be lower than if the patch is describing a sharp feature or a curved region. So, we propose to find this subset, solving an optimization problem, such that we have to find a subset X prime included in X, where any 2 points, the normal difference between any 2 points contained in X prime must be minimum. So now here we'll have a crisp subset X prime as solution. This is an example where the red triangle represents the subset X prime. But the problem with this formulation is that finding a solution to this problem results in an NP-hard combinatorial complexity problem. To solve it, to relax this problem, we propose to use a membership function such that this membership function defines the degree of inclusion of one point to the patch. So this function goes from 0 to 1, where 0 means no inclusion and 1 full inclusion. So now instead of finding a crucial subset X prime, we want to find this function u defined over all the domain X, such that we want to minimize the normal difference between any 2 points contained in X, but weighted by the values of the membership function. Now we will have a solution like this, which is fuzzy. In the discrete setting, a solution will look like this, where blue is 0 and red is 1. Here we have a patch with higher than the patch here, which has 0 error because the normal is constant. But also a solution is a 0 area patch. To avoid this kind of solution, we add a constraint such that the area of all the shape X weighted by the membership function u must be equal to a defined area that it's set that we set as a parameter. So this is a fixed value. All patches will have the same area. So this is a patch, but we can have a solution. The black point is the reference point. We can have a solution far to the reference points, or more complicated, irregular solution like this. So to solve the first problem, we penalize the distance between any point of X regarding the reference point, and weighted by the membership function u. So using this term, we will have solution closer to the reference point. This is an example on the left without using the term, and the right using it. But also we have the problem that the solution is irregular. To solve the irregularity problem, we propose to use to minimize the gradient norm of u, such that giving more importance to this term, we will obtain more smooth solution, which results in more regular solutions. So this is an example where when increasing the influence of this term. We have another problem because we can have a solution that lies in the incorrect phase of the shape, because this patch, which is in the incorrect phase, has an average normal too different to the reference point. To solve this problem, we propose to penalize the normal difference between any point of the domain X regarding the normal of the reference points, weighted by the membership function u. In that sense, we will obtain a solution which has coherence to the reference point norm. So we have this optimization problem where we have the parameters alpha, beta, gamma, and delta that allows us to control the behavior of the patches. These are examples of how patches work. So our denoising algorithm is based on first computing the adaptive patches, then we filter the normals using these patches and including a bilateral normal filtering step, which allows us to obtain smoother solutions. This is an optional step, and then we update Bert's position using the new normal field. So the filtering based on the patches is just an average normal regarding using as weight average weight and normal using as weights the corresponding values of the membership function and the area of each triangle. And in the case of bilateral normal filtering, we use as a spatial distance the distance between the centers of the triangles, and a signal distance the distance between the normals of the corresponding triangles. The Bert's updating step tries to minimize this energy function such that the new normal NF must be orthogonal to each edge of the triangle defined by the corresponding vertices. So we have to find the position of these vertices. Trying to solve this, to approximate a solution to this, to the minimization of this energy function, several algorithms were proposed. We just use a proposal, one of the most used proposals, which consists of this updating step. So we first compare our method using the optional step. We have an original mesh, then we added noise, artificial noise, and then we clean the mesh without using the optional step, and then using it. As we can see, using this step we obtain smooth solutions, but if we look at the numerical results, where the first metric represents the distance between two surfaces, the second one between the corresponding normal fields, the third one the distance between the curved fields, and the last one the volume error, we can see that our result without using this optional step is more close to the original one, because it has some flat patterns that are too smooth in the result that uses this optional step. Then we try to compare our patches, or average normal of our patches, with the average normal of the patches proposed in this work, and we obtained a lower error than normal error than the normal proposed by there in this work. In fact, we have the error obtained by there. Trying to evaluate performance, we found that the execution time of the most costly execution time of our algorithm is the computation of adaptive patches, but it has a linear growth because in practice we restrict the domain the domain X to be of a constant size. We define a maximum number of triangles to include in the domain, so we compute the patches over a small neighborhood regarding the reference point. So here we have an example where we have an original mesh, then we corrupt it with artificial noise. The last one is a result. As we can see, we maintain some patterns that are included in the original one, but other algorithms clean smooth to match these patterns and removes them. We can see it in the numerical results, where we obtain the lowest metrics regarding mesh distance and normal field distance. Also in the other metrics we have results close to the lowest ones. So this is another example where we preserve better this sharp feature, the line, and this is also visible in the numerical results, where we obtain, in the case of the normal, the lowest one, and in the other cases close to the lowest one. Using real data obtained from 3D scanning, we can see that the first one is the noisy mesh and the other the results. The last one is our result. We can see that we preserve some patterns of the original mesh. We can see better here where these pattern of lines labeled sets are more defined in our results here, which are the last few. The other iron is blurred to match these details. This is another sample. We can see in general that we preserve most of the details of the original maze while removing the noise. And here's an example where we used two configurations of our mesh. We first configured or are going to remove the staircase artifact, and then we denoised the output of this filtering step, and we obtained the results. This is another example using the same pipeline. So our conclusions are that we obtained the lowest numeric error in most cases when using synthetic data. In the case of real data, we present better definition of details in most cases. Our algorithm is dependent on the choice of the optimization problem parameters. This allows the user to play and occur different behaviors of the final result. We, as feature work, we want to use the vertex normal field instead of the face-based normal field, or to combine both to obtain a more robust solution. Also, we want to use our adaptive patches in other applications like remeshing, segmentation, or feature detection. And we can use, instead of the normals, we can use another descriptor, for example, like the curvature or saliency, heat kernels, or others. That's all. I think that here are some reference, and thank you very much.